Okay, let's play the
You didn't notice that? You didn't notice that? Oh, there's so many.
There's so
Okay, amazing job, team. You guys can all sit down in the front now.
Okay, can you guys hear me? Okay. Okay, everyone can hear me okay? All right. Okay, are you guys ready to begin? Work on some Ochem? Yay! All right, so the first thing we'll be talking about are shapes, bond angles, and hybridization. So you have a nice chart here at the front. I'm just going to label a couple things here just so it's easier to read, especially the part talking about notation and shape. So here you see A equals the central atom, X equals the peripheral atoms. So you see here that we got A that was bonded to two other atoms. Sorry, my handwriting's terrible. That means it's linear. If it's trigonal planar, if I can talk, you got an atom bonded to three other atoms. If it's bent, you got an atom bonded to two other atoms. And E is kind of confusing. It just means lone pairs. So I'm just going to draw those in. That means it's bent. Tetrahedral is an atom that's bonded to four different atoms. You guys probably already know this stuff. I just want to draw it out before we get into the material. And then trigonal pyramidal is an atom bonded to three other atoms with the lone pair. And then bent is an atom bonded to two other atoms. And then you got two lone pairs. So if you guys haven't already memorized this, it'd probably be good to kind of look at this chart, make some flashcards, or just practice writing it down because you will see stuff like that. Okay, so getting to the problems themselves. So first we're starting with SO2. So what I like to do, finding the valence electrons, is write out the different atoms. And then I write how many of each that we have. So we have one sulfur atom, two oxygen atoms, and then figure out the number of valence electrons. So, and just so you guys know, on the test at the back of it, you will have a periodic table. So if you forget that sulfur has 6 valence electrons, it is totally okay. You'll have that there so you can figure it out. So 1 times 6 equals 6. 2 times 6 equals 12. So 6 plus 12 equals 18 valence electrons. And just another note, a lot of times oxygen have two lone pairs and be double bonded to something. So you kind of keep that in mind for this example. So we'll write, so I got the eraser going. So write sulfur with 2 oxygens coming off of it. And then if you count the lone pairs, you'll see it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we haven't actually gotten all of the valence electrons in there. So those actually go on the sulfur. Sulfur can have more than, it can have over a full octet. It can have 10, 12. It can be a little bit crazy sometimes. Same thing with boron. It can be a little weird. You guys might have seen this in the homework that like you had BF3, and in that example, it actually didn't even fill its octet. So just watch out for boron and sulfur on the test. They're the big ones. So now to calculate hybridization. So what I like to do is look at the groups attached to the sulfur. So you will see here that sulfur is attached to 2 atoms and it has 1 lone pair. So 2 plus 1 is 3. Then to get the hybridization, you just subtract 1. So 3 minus 1 is sp2. Another thing to keep in mind is something's sp3, The bond angle is 109.5 degrees. SP2 is typically 120 degrees, and SP is 180 degrees. So in this example, we got this SP2 atom, like I said, and well, its bond angle is 120, but one thing you have to watch out for is if there's a lone pair on the atom, that means you have to put a less than sign out in front. So I'll just write lone pair. Sorry about my handwriting again. You need to put a less than sign. Okay, and then shape, you can just look at the graph up here. So the shape, we see that it is bent. It's this one right here. I don't know if you guys can actually see that pointer or not, but bent. Okay, going on to the next one. We have NO2 plus. Watch out for the plus. I like to circle things just so I don't forget. So we'll just kind of go through the same process again. I'll go a little bit faster this time since you guys probably got this down. So nitrogen, 2 oxygens. So it is 5, and then 2 times 6 equals 12. But one thing you have to watch out of, because of the positive charge, you actually subtract 1. So it is 16 valence electrons. So what we'll do in this example is have the nitrogen. Like I said, oxygen likes having that double bond and the 2 lone pairs. So then you can count that up, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's always good just to double check and always remember to put that formal charge on it. All right. So in this one, the nitrogen is bonded to 2 other groups or 2 other atoms. So like say you do 2 minus 1 equals 1. So this is an sp atom. Then you can go up to the chart up here. Sp is 180 degrees. And there are no lone pairs. So you can see over here. So because there are no lone pairs, you do not put a less than sign out in front. And then you can look up here for the shape. So if you got an atom bonded to 2 other atoms, that is linear. Okay. Does that make sense so far for everyone? Okay. All right. So now going down to this bottom part, and I remember having something like this on my test, so I'd watch out for it. So first we are focusing on the C7 right here. So you can see that it is bonded to 3 different atoms. So like I said, then I do 3 minus 1 is 2. So this is sp2. Now this is where it's really important to read the instructions, because on this next one, it says the lone pairs of electrons are not shown. That's really important on this one. So when you're finding the hybridization of O1, it could look like it's only bonded to 2 things, but you have to remember to draw in the lone pairs. So it's bonded to 2 atoms. 2 atoms. You can see here, it has the 2 lone pairs. So this one, like I said, then you subtract, there's 4 groups, 4 minus 1 is 3. So it is sp3. Then this one, you have to be able to find the bond angle. So O2, C6, O1, which would be looking at this right here, but you look at the center one. So you calculate it, then you figure out, okay, this is sp2, because it's bonded to 3 different things. 3 minus 1 is 2. And if something is sp2, what is it? It's 120 degrees. So, okay, then the kind of the same process for this one. You got C4, C5, C6, which is this thing, but like I said, you really focus in on that middle one. So how many things is it bonded to? It's bonded to 1, 2, 3, 4. 4 minus 1 is 3, is sp3. So what is the bond angle? It is 109.5 degrees. So like I said, there's no lone pairs. Always watch out for that. And then O1, C7, 6, 8 bond angle. You can see here that this one we actually already figured out. It was sp2. So this one would be 120 degrees. Okay, and then which carbon is the primary carbon? So primary carbon just means that it is bound to one other carbon. Secondary would be bound to 2 other carbons, tertiary would be 3, quaternary would be 4. So this one, which carbon is bound to primary carbon? I would just look over here, start with the first one. And you can see this first one actually already answers it for us. It's only bound to 1 other carbon, this one. So that makes it pretty easy. So this one's C1. A couple of the other things to keep in mind that I had on my test, so I was glad one of the TAs clued me in on this, was, of course, if you have, you guys might have remembered this already, but if you have a carbon bonded to another carbon, it's a single bond, that's the bond length is 1.54 angstroms. If it's a carbon double bonded to another carbon, it's 1.33 angstroms. And then if it's a carbon triple bonded to another carbon, it is 1.20 angstroms. I would keep those numbers in mind because I remember I had a chart like this, but I did actually have to answer a question of that sort too. Like I said, there's actually one other question on this page. So circle all atoms. This must lie in the same plane as C6. So first off, well, you go ahead and circle C6 then. And for these type of problems, you look for the double bond. So you circle the 2 things in the double bond, and then you look for what's directly attached to the double bond. So O2 doesn't have anything else attached to it, but the other atom that's in the double bond attached to it, and a C5. So that's how you solve those types of questions. You look for the double bond, look for the atoms that are attached, that are in the double bond, and then you look for the atoms coming off of it. So let me check to make sure I did it correctly. But yeah, that's the first page, guys. So, oh, about took the microphone with me.
Okay, give me a minute for like 3 minutes.
Oh,
And then I'll come back at like 7.
Hold on.
okay, yeah, all right.
Okay, 3-minute break. We'll start at like 7:21 again. If you have any questions, raise your hands. We'll come up to you. Question? Is that? Those are all, is it because it has to be a single bond? Like, why is it
For
carbon?
this one, let me look at it.
You wanna answer this one?
Well, never answered that question. there.
Um,
Circle all atoms in a line the same time as 6.
No, she did.
yes, yeah, I answered that question, but
No.
yeah, of course, like good question. Let me look at this because the answer key says that it's C1, but let's just go through this because it'd be good practice too. All right. So the C1, if you look at it, it's bound to 1 other carbon. That's a primary. This carbon is bound to 2 other carbons, so that's secondary. The C3 is bound to 2 other carbons. C4 is bound to 2 other carbons. C5 is bound to 2 other carbons. And then I see what you're talking about. I wonder if the answer key is actually incorrect on this because C6 is actually only bound to 1 other carbon. And then if you look at C7 and C8 as well, that is the case. That is really weird. I might have to bring this up with Dr. Berg tomorrow and see what he says.
I think last year they said something, it was like sp3 hybridized carbon. So
So
like
it has to
picking,
be,
yeah,
okay.
we're picking between that.
Oh, okay.
Because you can't have an sp2 hybridized carbon that's like tertiary degrees, if that makes sense.
Oh, okay. All right. Yeah, thank you for catching that. That's great.
No, I think someone asked that question last year.
Yeah. Yeah, thank you, Gigi. So let me erase this. All right. Okay. All right. So did you say we're taking a 10-minute break?
No, 1 more minute break.
Oh, 1 more minute break. Okay. All right. Does anyone else have any more questions while I'm up here? Any questions? It has something to do with the other ones we believe being sp2 carbons. That the like C6, let me see here. C6 is an sp2 carbon, and you can see in this example, C7, C8 also are sp2 carbons. I'm gonna ask Dr. Berg about it before class, so because I'm really not sure on the reasoning for that. But yeah, it's great that you guys called that out. That's good. Okay.
Is it yours?
No.
Okay, whoever I think it is.
I was thinking,
Stop. I like
wait, so this one's to right.
this one's to right. Yeah, this is eraser.
Okay.
This is to like circle things like and disappears after a set.
Oh, okay, okay. So I don't have an iPad, so
Oh, I know you don't have an iPad.
it's my endless supply of paper.
Yes, I'm very grateful for it. Dun, dun, dun. Dun, 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 dun. Okay, we'll start on acids and bases when everyone's ready. All right, so starting off, we can see that there are two different definitions for acid and base this semester. So there's Bronsted-Lowry, which is just what you're used to, just a proton transfer. So acids are proton donors, bases are proton. You can see this hydrochloric acid, it loses that hydrogen, indicating that this is being donated. This is the acid, and this is therefore the conjugate base. You can see that the water is accepting that proton. So this is the base, and this is the conjugate acid. Lewis acid and Lewis base. So it's basically like switched. So the acid is going to be the acceptor, but it's going to be a lone pair acceptor. Base, lone pair donor. So you can see in the example next to it that iron is accepting that lone pair. It's a lone pair acceptor. So this is the Lewis acid. I'm just going to write La. And this is the Lewis base. And you can see it forms this like kind of complex. This is just the acid and that's just the base, basically. Okay, and label the acids and base in the following equation. We can see that the HF is losing that hydrogen. This is donated. Therefore, this is the base, this is the conjugate base, and this is the acid, conjugate acid. Yeah. The following is the Lewis acid. This is probably the most confusing question on this page. So I would just start with drawing out all the molecules. So carbon. And I would also really recommend like learning formal charge, like just understanding it really well, just because that will help you out a lot just throughout college. This is so our definition of a Lewis acid was it's a lone pair acceptor. So out of these four, starting from methane, so CH4, that carbon looks pretty happy as it is. This is ammonium ion. Yeah, ammonium ion. It has that positive formal charge, but since nitrogen is a little less electronegative than the other electronegative atoms, and OF, it can hold that positive charge decently well. So it's happy as it is. And then we'll skip over to the carbon also looks pretty happy. This oxygen has its lone pairs, no formal charge. So what we're kind of left with is this carbon. This is the third option where it doesn't have its full octet. It only has 6 valence electrons. So it will be very happy to accept that lone pair to kind of fill up its octet. Any questions on that? Okay, looks good. So determining acid strength. So this is the list we're going to be determining them by. So like first you're going to go by size, electronegativity, et cetera, et cetera. So as size increases as you go down the periodic table. So, and as you size increases, the acidity also increases. The reason being, if we like compare HI, I skip right, but whatever. Iodine, HI has like the longest bond out of all the whatever halogens. So it's basically easier to break longer bonds than like if it was a bit shorter. So that's just the reasoning being, but you don't really have to know that. You just have to know bigger size is more acidic. Next, the criteria is so it increases from left to right. So this is comparing them from the same like period. I think that's period, yeah. So electronegativity example, we get to that example, so give it a sec. Hybridization, this is a little bit tricky, but if you look at the hybridization of carbons, sp carbons are, the pK is about 25, sp2 is about 40. P3 is about 50. So those are their pKa's generally. So you can see that the sp carbon has a lower pK, indicating it's more acidic. So that's just the trend. Hybridization isn't super big, but inductive effect is. So inductive effect is basically just like, okay, OH, okay. Pretend like these are the same number of carbons, which I think they are. But inductive effect is basically saying if you place an electronegative atom close to the like group where the atom where the proton is leaving, so like this OH group, the closer it is, the more acidic it is. So this would be more acidic than my other option. Reason being that chloride is pulling all that electronegative electron density towards it, which makes it a little bit more positive, this hydrogen, so it's kind of easier to pluck off, if that makes sense. And finally, resonance structures. I don't think you guys have gone to resonance at all, basically, but the easiest explanation is a carboxylic acid versus just an alcohol. So you can see that in the carboxylic acid, the pK is about 5, which I think you guys are expected to know. The pK is 15 for alcohols. So what happens is if you look at the conjugate bases, that this pair of electrons in the pi bond can kind of like go down. Resonance is denoted by a double-headed arrow. And then so it like, so this basically just stabilizes it. A more stable conjugate base is a stronger acid, I believe. So that's why resonance structures make the acid a bit stronger. So like carboxylic acid pK is 5 and this alcohol. So which of the following is the strongest acid? We can see that we're comparing these atoms. So that's oxygen, sulfur, and selenium. These are right next to each other. Okay. We don't have a periodic table, but I assume you all know that oxygen, it's like oxygen, sulfur, selenium. So selenium is the largest size. We're going up and down. So therefore, this is the strongest acid. Make sense? Okay. And which is the stronger base? So this one, we find whatever is the stronger base through whatever is the weaker acid. So acid. So if we compare HCl and HBr, that's also a size difference. So Cl and Br. This is the stronger acid, so therefore it's the weaker base. And this is the stronger base, vice versa, weaker acid. So this is going to be that chlorine ion. Sounds good? Okay, so now we're going to do equilibrium. So NH3 and NH2. This is going to be the acid, because you can see that it's losing that proton, that hydrogen. And so therefore, this is the base, this is the conjugate base, I write that down. And this is the conjugate acid. This is a spectator ion, we don't care about that. So the acid on the left is write NH3, acid on the right, H2O, the stronger acid. We compare pK, so let me find that. Okay, the pK of NH3 is what I have in my notes. 38, and pK of water, which is 15.74. The stronger acid is going to be the lower pKa. So that's going to be H2O. Therefore, the weaker acid must be NH3. Equilibrium goes towards the weaker acid and the higher pKa. Yeah, which is NH3, so therefore it goes left. Remember, a true equilibrium, that is, I think if it's 3 or below, so less than, or equal to 3, then it's gonna be equilibrium. Just watch out for that. For pKa, remember that the lower the pH, which is which is higher acid strength, the Ka is higher, and the pK is the negative log of the Ka, which is lower. So this is like kind of like the general trend thought process. Any questions? Okay, sounds good. We'll do another like 3-minute break. We'll come back at like 7:35, and then we'll do the next page.
Kim, if I send you like something, can you add it to it? I have like kind of like counters.
There were so many questions last year session.
There's also like so many less people this year.
Yeah.
There's only one class.
We get like, oh yeah, true. Last year there was like really 2 days, really. Did you send it?
Yeah. I can.
Is it this?
Yeah.
Then you just want.
I'll just go over it like real quick and then I'll.
You wanna like write on it and stuff?
Nah, I'm
Okay.
low-key just gonna read it and
Okay.
quick, I guess.
Yeah.
And then the next part I'll just go back and then.
Yeah.
Oh, your notes are so good.
What time did you say?
They're nerds, sorry.
What time did you say?
35.
Are you safe?
Now I'm hungry.
You say.
For what? For your page? Maybe I'll come back. For what, naming? I can name already. What do I need it for?
That's so true.
Yeah.
That's not true.
That's not true.
Yeah. Low-key, things be falling out your brain.
Yeah.
Like,
Especially like the alkene, easy.
oh my gosh, I have to
do
relearn it
that.
every single time. I'm like,
It's so bad. But you'll never be tested on it.
I'm like,
again.
well, that's probably not true. I might have to retake MCAT, so I will be tested, but. Okay, guys, can you guys hear me? Okay, so it's 7:35, so we're gonna get back into this. My name is Harper. Real quick, I just thought that I would start off with like kind of a review of everything I think you need to know for this section. So bear with me if it's like redundant. But so first, like I kind of made this cheat sheet. We can send it out like after. So for Newman projections, like when you're looking at it, the back carbons are always going to stay the same when we're looking at that kind of like configuration. The things that change and like what we can change are the front ones. And then for cis versus trans, cis means all molecules are on the same plane. So like dash dash or wedge wedge. And then like in the Hayworth section, Hayworth structures, it's going to be all molecules are up or all molecules are down. And then chair, all molecules up or all molecules down. So it's like kind of the same. So up, up, down, down. And then right now, just pretend equatorial and axial like doesn't matter. And then when we talk about trans, molecules are on different planes, so wedge dash or up down. And then in the Hayworth, they're going to be opposite of each other, so up down or up or down up. And then in the chair position, it's going to be the same, so up and down. They're not going to be like facing the same way. And do not like consider equatorial or axial right now. All we're thinking about is up or down. So now when we talk about ring flips, things that stay the same are going to be the direction. So if something starts up, it's going to still be up. If something starts down, it's going to still be down. And then what's changing is the spatial designation. So if it starts at axial, it's going to become equatorial, but it's going to still be like relative up to where it was before. And also hashtag size matters, but big groups want equatorial because there's less steric terrain. So if you have a question where it's like, which one's better? Like it's going to be the one where the biggest group is in the equatorial position. Like I guarantee that's probably going to be a question, and that's just because there's less steric strain. And talking about strains, this is important. They will ask you questions about strains probably. So torsional strain is going to be present in eclipsed and Newman projections, and in some cycloalkanes. It's just when it looks like that. And then steric strain is gauche in staggered Newman projections, and then flagpole in boat conformations. And I think I have a quiz that I can send out to the group chat. It's really helpful because some of this stuff is like kind of small. And then 1 through diaxial in chair conformations with methyl groups in axial. So if the methyl group is in equatorial, there is not going to be a strain, but because it's like up, it's really big and really annoying. And so really quickly, like bond angle strain review. So planar cyclohexanes in most cyclic structures, except for cyclopentane. So all these are planar. And then just a review like torsional strain, bond angle strain, and not just because like our ideal hybridization like is going to tell us that we want a bond angle of like about 109.5, but this is like forcing it to go beyond that. So that's why we have those kinds of strains. We're forcing the electron clouds to like be closer together than they want to be. So they're going to repel against each other and lead to all these strains. And so in the boat conformation, there's torsional strain and steric strain, which is the flagpole strain. And then when we flip to that kind of chair position, there is no strain unless there is the methyl group in the axial position. So yeah, I hope that helps everyone. I can send it out again. So now we're gonna get into the fun stuff. Okay, so first things first, I'm just gonna write down when we have gauche, it's steric strain that occurs when alkyl groups are near each other. And so we're going to just start off by like translating this little structure thing to over here. So when we first draw these, we just want to make sure that we keep the back in the back the whole time. So I just like to go about that by just drawing it the same in every single one. I start with the back ones. And honestly, it doesn't really matter which like way you orient it from here. I just like to keep it in this generalized position. And then I'm just going to kind of highlight it. And so this is always going to stay the same. We cannot rotate this. Okay, now the new stuff. So that's what we have in the front. And I'm just going to start with this group right here. And then I'm going to kind of color code it. So now when we move to the next one, literally all we're going to do is rotate like one down. So now this is here. And then we're going to rotate it one more time. So now this is 320 degrees, 180, and 60. So now we're going to kind of approximate like how much strain is going on in each of these different conformations. So I believe ghost strain is about like 0.9, whatever the unit is, 0.9 of strain, whatever that means. So I just like to denote it by like this is like about 0.9 like ghost strain. And then this is going to be like more than 0.9. And that's because we have that like giant like ethyl group next to the methyl group, and that's like really big and really inconvenient. And so now we're gonna look at this one. So these are like pretty big, but not as big as the other ones. So that's about 0.9, 0.9. And then we have the super duper ghost strain going on right here. And like the kind of medium one. So when we look at this, these are about like these two are about the same amount of bad, right? The one with the least amount of energy is going to have the least amount of ghost strain. And so it is going to be this one. And right here, this is like the highest because it's eclipsed. Okay, and on like this, you can definitely rotate it on your own. But this is like a perfect example of when to use your model set. So it could be helpful here. That way, like you're not like messing it up in your brain or anything like that. Like literally all you're gonna do is like rotate it like a little clock. It'll be so helpful and so awesome, I promise. So now let's get into the fun stuff, the cyclohexane chair conformations. So some things to remember. Large groups in axial positions are going to have hella steric strain. And also like lower energy is going to be more stable. Okay. So now we're going to look at this and we have a little name. So it's cis, important to remember, 1-ethyl, 3-methyl cyclohexane. So you can, again, as long as you start where you start and remain consistent, it doesn't really matter. Like I could start like the like ethyl here and like the methyl like there, but I'm not going to. So I'll start here. So this is going to be our 1 position, and I'm just going to draw our little ethyl group here. And then 2, 3. And I could have started like with wedges. It doesn't really matter. Or with dashes, as long as it's cis. So as long as they're on the same plane. And then here's our methyl group. And now we just have to translate it to here. And we need to remember, don't forget to draw the hydrogens. So CH2, CH3, our little methyl group, or our ethyl group right here, and then our methyl group here, and then our hydrogens. And because it's this, we either could have drawn it up, up, or down, down. So it doesn't matter. But I just always like to start with up if they're cis. Doesn't really matter. And so now we just have to translate it to here. So this is going to be our up color. And so we just have to start up for both of them. And then our hydrogens, and then our methyl group, and our other hydrogens. And again, do not forget up and up. And so now when we have our magical chair flip, it's going to stay up. What starts up is going to stay up, but now it's just going to go from axial to equatorial. That's literally the only thing changing. So and so it says circle the more stable chair conformation. So out of these two, this is like terrible and bad. We don't like that. That's going to be like really high in energy and it's going to be really unstable. It's going to immediately flip back to this one. So this is going to be our more stable one because it has the lowest energy. And then just one more time. The direction is going to stay the same. So like up to up or like down to down. And then what's going to change is the spatial designation. So either equatorial or axial. Okay. Yay. Does anybody have any questions? Yeah. Like for this part, I just generally like if I draw it up on this one, I believe it has to be up on the second one, if that makes sense. Like, what do you mean? Like if I started with it down, then are you talking about the ethyl group? Like if the ethyl group was like here, then we would start with it like on the down position. It technically I don't think it should be wrong as long as you like as long as you show the concept, but I think it just helps like keep things straight in your brain if you start up like here. Um, to start up there, if that makes sense. Okay, does anybody else have any questions?
For the conformations, if you don't have like two ethyl groups, if you have like an ethyl group and then like a hydrogen, does it matter which side you put them on? Like two or three?
Like for this one?
Yeah, like one of those CH3 was like a hydrogen. Does it matter if you put it on like either side?
Like if this was like a hydrogen.
Yeah.
Yeah. So I would recommend like keeping it in the same like 1, 2, 3. And then like you write it out like 1, 2, 3, like in that hydrogen.
Like a skeletal structure.
I don't think they will have you do that on this test. As long I don't think it matters that much. As long as like Yeah, I don't think it matters that much. Okay. Do you want, who's next? Okay, you're next. Okay, cool. Okay, we're gonna take a 2-minute break, so 7:53. Yay.
Sorry, I'm just making sure that.
Sorry. Let me just get out of the way.
I pushed my meeting. So I was like, I want to actually help out. I had my team, but it's fine. They're doing it. So. Yeah.
Just right on this then. That makes sense.
Yeah, it's just continuous for all the.
Yeah.
What are you doing? Okay. Is that nomenclature? Oh, I'm sorry. They're gonna hound you with question orders. You're gonna get the most amount of questions.
I just realized normally we'll like rotate.
That makes sense. Oh,
I had to take a bio like in one of the stickers like our plans about any like they gave us like and so it's like in my mouth.
Wait, what time are we starting? 7:55.
I mean, it doesn't really matter.
Oh, okay.
I just like to get it like one of the friends.
That's smart.
He's not the one.
Oh, I know. Oh.
Are you in the group?
Yeah. Then, well, we'll see what I am, but she doesn't want to.
Okay. I just want to make sure you can see the group. All the stuff is really confusing. Are you technically getting oh, no, and did you just
No, I didn't.
Okay, we're gonna get started on nomenclature. Can you guys hear me in the back? Just want to double check. Okay, cool. I've never used a mic like this before. Okay, so we're gonna start with the nomenclature. Personally, one of my favorite parts of Orgo. I'll try and make this interactive because I think the best way to learn nomenclature is when you're practicing. So do just call it out when I ask. So just to start off, we're gonna look over here. So your common alkanes. So a key thing to note right away, highlighter, talking about alkanes. So don't worry about double bonds, don't worry about triple bonds in this page. We're just talking about single bonded carbons. So that's the start of that. So we have the prefix. So just telling you basically the number of carbons. So you have methane for 1, ethane for 2, propane for 3, and then the rest are your regular prefixes. You just have to memorize the first 4. I think someone had like monkeys eat purple bananas to help you remember those, and the rest is just like your regular pent means 5, hex means 6, and so on. So I can write that down because that is pretty helpful sometimes. It saved me on the first exam. So monkeys eat purple bananas. Yeah, okay. So let me quickly get this. Oh, my first time using this thing here. This is interesting. Okay. But yeah, so it's just the regular naming the parent function. So put your prefix, put your suffix. It's going to be ending in ane if it's just an alkane, single bonded carbon only. So over at the alkyl groups, this is when your alkane becomes a branch. So we had this side as the parent, and this side as the branches, which it says right there. So let me highlight that in a color that's probably a lot easier to see actually. Let's see. Oh, okay, good. It shows up. Nice. Okay. So yeah, branches, similar thing is just going to be like your prefix, but now the suffix is different. Instead of ane, you have il. That just indicates that it's a branch. So we have methyl, ethyl, propyl, stuff like that. And then, but yeah. So is everyone fine on that part? Yes. Okay. All right. So now we'll get started on the fun part. Okay. So what is the first thing you're going to do when looking at nomenclature? What do you want to first find? Yes, the longest parent chain, exactly. So for this case, this is the longest parent chain. Some people have the habit of going down the straight chain. Like they're like, oh, okay, just go down the straight chain. That's probably the longest one. That's not right. This is 4. The other one is 5. We want the higher number. So please be careful about that. On the exam, you're gonna have like zigzags. Don't just go for the straight line. I promise you, majority of the time, it's not gonna be the longest chain. So highlight it. Bring highlighters with you to the exam. Super helpful. I know it seems redundant. You think like, oh, this is gonna be so easy. There's no way I'm gonna miss a carbon. And then you end up missing 3. So bring a highlighter. But yeah, so this is the longest chain. So am I gonna start, actually here, just number both. So you wanna number it down from the end. Oh, my handwriting is so bad. Okay. And then I'll do the red color. 4, 5. So we want to pick the lowest numbering. So let's see, we have the blue, which is 1, or sorry, no branches on there. So you do the numbers by the branches. So we have 2, we have 1 on 3, and that's it for the blue coloring. Now, if we look at red, we start at 3, and then we have it at 4. Is blue or red, which one contains the lower number? Yes. Yes, you guys are right. The blue one, perfect. So we're gonna go down the blue numbering because we don't have a functional group. There's no priority going on. They're both methyls for the branches. You want the lowest number, period, on that. So that's the branches we're gonna use. So whenever we're writing down the same branch, remember putting the numbers first. 2, 3. We're very strict on punctuation. Don't forget your commas. Don't forget your dashes. If a number's in between words, put 2 dashes to separate it. So yeah, dash. Okay, what is my branch name gonna be here? How many methyls do I have? So I have dimethyl, because we have 2 methyls. So dimethyl. And then what's the parent chain? I heard it, pentane. There are 5 carbons. So yeah, there you go. 2, 3 dash dimethyl pentane. And that tells you everything you need to know. So yeah. Okay, we're gonna go on to the next one. Like I said, zigzags are very annoying. We gotta be careful. You went down the straight chain, you're missing these 2 up here. And you're also missing that end right there. So the longest chain has 1, 2, 3, 4, 5, 6, 7, 8 carbons, not the 5 that would have been from the straight chain. So please be careful now in the exam. Let's do numbering second way. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's look for our branches. Start with the blue. We have a branch on number 3 and 4. And then if we go down the red, we have a 5 and a 6. Which one's the lowest number? Yes, blue. I'm trying to wake you guys up right now. I know it's 8 p.m. on a Sunday night, but we got this. You guys got this. Woo. Okay. So yeah, that's our lowest numbering. We want the lowest numbering for the branch. That's our favorite thing, as long as there's no functional group, once again. So what branches do we have? I heard there's an ethyl, yes, and there's a methyl right there. So let me write that down. Our ethyl group in orange. And our methyl group, I'll put it in blue because why not? Okay. We're looking at the blue numbering, right? So we want that 3 and we want that 4. 4 goes for the ethyl, 3 goes for the methyl. Remember, make sure you put your 2 dashes. We will give you a point off if you don't put 2 dashes. Got to separate numbers from words. It's a given like rule you have to. So yeah. Another thing I do want to note, sometimes people get confused about like the numbering. So, ethyl comes first alphabetically instead of methyl. So sometimes people are like, oh, like, why don't we go for a lower number on that? Not in this case, it's not like an example of that, but some people usually ask that. You have to just go by lowest numbering overall. Doesn't matter if that branch name comes first alphabetically. So lowest numbering, that's the priority here. So yeah. And then we have 8 carbons. So what's the parent function? Parent name? Yes, octane. Octane. Yes. So there's that one as well. Okay. Now we have it in just bond line. So we don't actually draw out the carbons. So sometimes a little bit tricky. But remember, wherever you see like the elbows or the ends has a carbon, has a methyl group technically. But yeah, okay. So start with numbering at this. Oh, actually, let's highlight it first. Highlight the longest chain of carbons. And then we're going to number starting from each end. 1, 2, 3, 4. Okay. So let's start with blue. We have a branch at 2, we have a branch at 3, we have a branch at 2, and a branch at 3 for red. Is either greater than the other or less than the other? Are they different or are they the same number? Yes. So we don't actually have numbering priority here. We have to do it differently. What priority we're going to give it? Yes. Yep, exactly. You guys got it. So we have, let me see, this is oh, nice. Okay. We have a flora and we have a chloro. Which one comes first alphabetically? Yes, perfect. So because of the fact that the numbering is the exact same, we're just going to give priority alphabetically, like you guys mentioned. So that chloro is going to come first with the lowest number. So we're going to give it the 2 chloro, and then let's see. Oh, I just made it red now. Okay, 3 fluoro. If we have 4 carbons, what's the parent chain? Yes, we got it. Butane. Oh, should be probably consistent with my color coding. My bad. Here, fluoro in green, fluoro in orange. Okay. So moving on to another zigzag. I'm going to highlight the longest parent chain. Start up there, go down there. So once again, I'm going to number from each end. 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. Okay. So let's look at the branching numbers. We have 3, 4, 5. And then for the blue, we have 3, 4, and 5. Oh, are they tied? Yes, they are. So once again, we're gonna have to look at what rule? Yes. Okay, nice. So which coloring gives the bromos the priority and lowest number? Yes, exactly. So we're gonna go with the blue because we want to do alphabetical because they're tied. They're the same numbers. It's pretty simple, but like be careful whenever you're doing this on an exam. I promise you sometimes like tiny errors will happen, but yeah. So yeah, we're gonna do 3, 4 because we have 2 bromines. Put that dash. What am I gonna put in front of the bromo? Yes, exactly. 2 bromos. And then we're gonna put the 5. What's this branch name? Yes, it's methyl. Methyl. And then we have 7 carbons, so the parent name is, yes, heptane. Nice. Heptane. So yeah, there we go. Now, ooh, we're on the cyclos. Cycloalkanes. Okay. So just a good rule of thumb, always count the amount of carbons on the branch, just in case. Sometimes if it's longer, then that longer chain is actually the parent group, no longer your cyclohexane or cycloalkane. But in this case, we have 3 carbons versus 5. So the cycloalkane is going to take priority for the parent name, basically. So, all right, now we're going to do the number order. 1, 2, 3. I'm just going to number up to the branches because we don't really care about the other side as long as we have the branches. And then 1, 2, 3. You guys can probably already tell that the numbering is the exact same. So what is this branch name up there? Yes. Does propyl or bromo come first alphabetically? Yes. So we're gonna give the red numbering priority because it gives the 1 to the bromo. So we're gonna start with 1 bromo and then branches in red, I guess. 3, bless you. Propyl. Okay. What is the name of the cycloalkane in this case? How many carbons do we have? So then it's going to be, yes, I heard it. Cyclopentane. Whenever it's a ring, you have to put cyclo in the front to indicate that it's closed. And then you put your regular name at the end. Sorry, my handwriting looks so bad in this. Oh. Cyclopentane. So your regular parent name after cyclo. But yeah, that's treated just as normal. The branches are listed just like how you would for a regular alkane. Not a huge difference there. Okay, now we've got another chain. You guys can probably tell this is cyclohexane. All right, let's do the numbering. 1, 2, 3, 4. Or we do 1, 2, 3, 4. List out branch numbers. 1, 3, 4. Which one has lower numbering? Red or blue? Yes, red. Nice. So there is no functional group here, so we're only looking at numbering. So for all of these, there was no other functional group than an alkane or a cycloalkane. That's why we're just looking at numbering. Had there been an alcohol, you have to give that one the priority numbering, even if there's like a whole bunch of branches on the other side and like one alcohol group. Like for example, we'll probably go over this in like the next slide, so don't worry about it too much, but like say you had like a whole bunch of branches here, like BR, chlorine, all that, and like this, yeah. If there was an alcohol down here, you would have to start numbering it from the right side because that functional group needs to take priority with numbering. So we don't really care about the fact that there's a whole bunch of other branches closer to the other side. But yeah, once again, we'll go over that in more detail on the next slide, so don't worry too much about that right now. Yeah, it's just regular numbering for right now. We're just trying to see for the lowest in general. And so once again, we go for lowest numbering. We don't care about alphabetical unless there's a tie. In this case, red is lower than blue. We go with red. Okay. So since we're going with the red numbering, I'm gonna put, we have an ethyl, we got a methyl, we got a chloro. So which one comes first alphabetically? Right. Yes, chloro, right? Even though it has the lowest numbering in the branch, still needs to come first. When you're writing out the words with the branches, right, you have to put in alphabetical first. So for chloro, even though it's the 4th branch, you want to put it first. For chloro, the next one, what comes next alphabetically? Yes. So you put ethyl next, and then you're left with methyl. And then, oh, I'm going off the page now. Put that down there. Fix that up real quick. And then what's the parent? Yes. Cycle. Exactly. Okay. Any questions? Kind of went through this pretty quickly. Oh. Exactly, yeah. So halogens have no priority. It's just like alphabetical when it comes to numbering being a tie, but they are not a functional group. You have an alcohol first, then comes the amine, and then comes your alkane. So do not give priority to the halogen. Same thing with methoxy. That's a good question to ask because that's a common trip up. So if you have your OCH3, right? That's a methoxy group. That also does not have priority. It's just a branch. So don't number it with priority in there. Just go for the lowest numbering whenever you're dealing with halogens or methoxy groups. Does anyone else have any other questions? Don't see anything. Okay, cool. Great. We'll take a 2-minute break, I guess. I don't think yeah, save a spot. Someone might just come down here specifically. Really, thank you so much. Great to know. This guy. You were going so fast. Good job on that. I knew you were yeah. Thank God, actually. I'm so glad. I think people like ask questions. I think it takes like 5 minutes, and then like more people were doing like the I think last time I like wrote out. Okay, that makes sense. We don't need it. Yeah, no, I don't think anyone wants to sit here until 10. I saw that time and I was like, it's in my mind, if we end before 9. Oh my God, I think we will. We're like 2 or 3 pages. There's 7. There's 7. Oh. I don't know. Yeah. Just 7. I hope I wasn't going too fast. I was like, people don't know. Also, the thing is, like a lot of people jump to their what they're doing. Yeah, that is true. Not paying attention. Yeah, that's super nice. The thing that I think it's like ages. Yeah, it's like 2 hours of recording. Girl, my laptop's about to explode. What? I know I'm so scared. This is 5. 5, and you're doing it. And then like, and then you're doing it. You're doing 7. Okay, I can put this higher up. Okay, can you guys hear me? Is this loud enough? Okay, let's get back into it. Okay, more naming. We're gonna start with some ethers. So the thing with ethers is we are going to replace the naming of like the ane is going to become oxy. So we start off. Let's find, first of all, our longest carbon chain, same as before, and then find our numbering. And if we do this numbering, 1, 2, 3, 4, or we could go in this direction, 1, 2, 4. Okay, so we can see that our light blue numbering or light purple numbering would be 2, 3 with our branches. And as for the other color, if I can find it, or we're gonna switch colors, I guess. Also 2, 3. So this leaves us with doing it alphabetically. So we have our ethoxy group up here, which is what I was talking about with, like, we know like ethane, butane, but that becomes oxy, so we know how to do that. And then our methyl group here, and our parent chain has 4 carbons, so butane. So if we put that all together,
then we know E comes before M alphabetically, so we would have 2-ethoxy, 3-methyl butane. Okay, awesome. Does that make sense? Perfect. So next we have our next ether, and we're going to start the same way we always do by highlighting our longest carbon chain. And by looking at this, we can see that if we go in this direction, 1, 2, 3, we would start with a branch on the third carbon. If we go in the other direction, 1, 2, 3, 4, it would be on the fourth. So 4, 5, 6, 7. So we either have 4, 7 or 3, 4, 5, 6, 3, 6. So we always want to go with our lowest numbering pattern, which would be this. So this is a methoxy group here. There's a methyl group there. And, oh, okay. So we would then name, alphabetically. So methoxy would come before methyl. And then 9-carbon chain would be what? Good job, guys. Okay, awesome. So something to keep in mind with ethers is that's just like any other group that we were looking at up here. It's like the same as like a methyl or, a haloalkane. It doesn't take any priority. It's just a branch. But that is not the case for the next group that we're going to look at, which is alcohols. So with alcohols, we always want a number in the direction that would give our alcohol the lowest number. And in this case, it's also the only functional group or branch coming off of it. So we would do it this way anyway, but that's just something that's good to keep in mind. So now we have 3 carbons here. So that would be propane, but we're going to drop that E because we don't want to have 2 vowels next to each other. Add a dash and then designate where our alcohol is. So propane 1, all. So alcohols are always going to have all, unless there's a priority functional group over it, but we have not learned that yet, so don't worry about it. So this one is redundant, which means that technically it's just propanol, but why not number it just in case? Okay. Next, we have this. We're always going to find our longest carbon chain. We also could have done it like that, but that's just doesn't look right to me, so I'm not going to do it like that. But it's the same either way. Then we are going to number, and even though this numbering scheme would give us 2, 3, 4, and going the other way would also give us 2, 3, 4. We're not going to think about it like that because we have our alcohol, and it's really important that we give that group priority. So 1, 2, 3, 4, 5, and then we have 2 methyl groups, which means we have to put what before the methyl? Exactly. So 3, 4 dimethyl pentan 2 all, because that alcohol's on the second carbon. Awesome. Any questions about alcohols? Awesome. Okay. Moving on, we are going to do amines. So basically, we are going to do the same thing that we did with alcohols and give those amines priority. So this is a 4-carbon chain, which means it would be butan
And then we're going to designate where that amine is, butan-1 amine. This would also be butanamine, just like how this was also just propanol, but I would just say like it's just better to include the number because then if it isn't redundant, then you won't get it wrong. Next, so I'll just write here that that's where you just put the end. Okay. Now we're going to find our longest carbon chain. It's just the straight chain, so that's super easy. And we're going to number in this direction because it gives us the lowest numbering scheme, which is always what we want. This is a 6-carbon chain, which means that it's going to be hexane. And then our amine is on the 2 carbons, so hexane 2 amine, but wait, I shouldn't have written it like that because we actually do have something that's going to come before that. And okay. Okay, so we see that we have this methyl group right there, and it's not attached to the main chain, it's attached to this nitrogen right here, which means that instead of putting a number as a locant, we're going to put the letter N. So N-methyl, and it's methyl because it's just 1 carbon there. Hexane 2 amine, there's not a space here. So just imagine that there's not. Okay, awesome. Does that all make sense? Perfect. Next, we're going to do branches. We don't have to worry about this one too much, but it is definitely good to have a basic understanding of. So basically, it's very similar to what we were just doing. You're going to find your longest carbon chain, and then you're going to number. And you're going to number in the direction the lowest number to the carbon that's attached to the main chain. So this like squiggly line is the main chain. And so that means that we're going to number like this. 1, 3, 4, because if we numbered in the other direction, then this carbon would be 3, and we don't want that because we want that to be the lowest one. So then we have 4 total, which means it's going to be butan, like we know, but drop the E, and then 2 because the second carbon is attached to the main chain, ill. And if this was being named in like an actual something with the parent chain represented, we would put parentheses around it, and we would put the number in front that is the locant for which carbon on the main chain this branch is attached to. But yeah, next we're going to do this branch. We're going to do the same thing, find the longest carbon chain, and then we are going to number it, giving the carbon attached to the parent chain the lowest number. And then we can see that this branch has branches on it, which is awesome. So we are going to look at what is attached to this longest carbon chain. And in this case, we have 2 methyl groups both attached to that carbon, the second carbon. So we're going to do what we've been doing and write 2,2-dimethyl propan, because there are 3 in the longest carbon chain, 3 carbons. Propan 1 ill. And that would all have parentheses around it. Does that make sense? Yeah, what's up?
Could it also be like terbutyl?
So technically yes, but you're not going to want to put that on a test, and you don't really need to know it in general just because we really focus on IUPAC naming, and that's a common name. But
Why don't we need parentheses for the like subsection?
oh, that's because this is just a branch. Even though it has the N, it's just kind of like if it was like 3-methyl or 2-methyl, it's just designating that's on the nitrogen. The only reason why we have parentheses around these is just because it's a branch, and it just has a different kind of convention. What's up? Could you put the, sorry, could you say it one more time? No, just because when it comes to branches, it's sort of like when we had like our alcohols or our amines, we're gonna put the number in the middle of the name, if that makes sense, as opposed to putting it before. So it would be like, as opposed to like 1-propanil, it would be propan-1-il, and that's just kind of convention. That's how we'd always do it. What's up in the back?
Mandatory to have it, then one on one.
Yeah, I would say yes, make sure that that number is between the propan and the all as opposed to putting it in front, because that can get but it's not. Since it's a functional group, it changes the main parent name, if that makes sense. Okay, other questions? Okay, now we're going to get into bicyclic compounds, and we definitely want to pay attention for this because I know that we've not really gone over this in class, at least not in Dr. Burr's class, and this might be on the exam, it might not, but in general, it's just a really good thing to know. So yeah, basically when it comes to bicyclic compounds, we are going to look at these, we are going to look at these carbons right here, and these are called bridgehead carbons. And you can kind of think about that making sense because they're kind of like bridging the gap between these two fused rings. So if you look at your bridgehead carbons, that's where you're always going to start numbering. And it's still going to follow all the same rules that we just learned about. Your numbering needs to be the lowest numbering scheme. Your numbering needs to prioritize functional groups and everything like that. But so the things to keep in mind with this is that you're always going to start your numbering at the bridgehead carbons, and you're always going to start numbering the biggest ring first. So the ring with the most carbons first. So in this case, we could either go in this direction with our numbering, or we could go in this direction with our numbering. In this case, it actually doesn't make a difference because this methyl group is in the middle here. So regardless of if we went around this way or if we went around this way, it would have the same number. So I'm just going to do it like this just because I want to, but make sure that starting with bridgehead carbon and starting with the larger ring. So now we have 8-methyl, just like we know how to do. And then we're going to write, just like how with cyclic compounds, we write like cyclo. This time we're going to write bicyclo because there are 2. And then we're going to count, okay, then we do a bracket. And we're going to write 3 numbers in this bracket, and they're going to be separated by periods. The first number is going to be the number of carbons on the larger ring. The second number is going to be the number of carbons on the smaller ring. And then the third number is going to be the number of carbons between the rings. So in this case, so with these numbers, yeah, actually, I'm not going to say that. That's going to be confusing. So in this case, we're going to count 1, 2, 3, 4. This has 4 on the larger ring, 1, 2, 3, 3 on the smaller ring, and then 0 between them. There are no carbons between them, and you don't really need to worry about that right now. So with this numbering, we're not counting those bridgehead carbons because that's the gap, like the fusing of the 2 rings. We're counting these outside carbons. Then our parent name is just going to be nonane, and we are, of course, going to count all of our carbons for that on the rings. So there are 9 total, nonane. I'm going to do the next one, and then we'll do questions. Okay, so we're starting at our bridgehead carbons, which are these guys right here. And then we are going to go in the way that is going to prioritize this alcohol, but also starting at the larger ring. So the best way to do that would be to go around like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And then we're going to look at our branches. We have a methoxy group right here, 5 methoxy. I'll try to write this small because it's going to be kind of long. Bicyclo. Our bracket. Now we have 1, 2, 3, 4, 5, 6 carbons in the bigger ring. 1, 2, 3 carbons in the smaller ring, and 0 between the two. And then we are going to, does anybody remember the parent name for 11 carbons? Undecane, I don't know. So we're going to write that, and we are going to modify this parent name because it's an alcohol. Let me actually write this a little bit smaller so I can fit it all there. And 9 all. And I want to make sure that that's really clear. Okay. Okay. Does that make sense? Any questions on any of this? Yeah, let's talk. Yeah, so the first number in the bracket, I'll write it here. Let's say bracket is going to be 1 dot number. Okay. Oops, actually there's not a period there, I lied. Okay. So the first number equals the carbons in the larger ring. The second one is in the smaller ring. And then the third number is the number of carbons between the two. Does that make sense? Not for the bracketed numbers. You're gonna count it for your like parent name just like normal, but for the bracketed, no. What's up? Could you say it just a little bit louder? No, all good. There of them? Oh, yeah. Starting at the bridgehead carbon, and we have to, so we're thinking about 3 things. 1, we have to, 2, we have to go around the larger ring first. But then 3, we also have a functional group here with this alcohol. We want to make sure that it has the lowest numbering scheme. So I'll really quickly go around the other way and show what that would look like. So always starting at these bridgehead carbons, of course. And if we went the other way, then this alcohol would be 11. So it would be undecan 11 all, and 9 is lower than 11. So we would want to prioritize that, if that makes sense. Okay. Other questions at all? They're periods. Yeah, so it's a little bit different than the other type of naming we've been doing. We actually put periods in between the numbers in the brackets. Wait, I'm just gonna renumber this so that we all have it. Okay, other questions? Okay, awesome. Then we'll do like a 3-minute break.
Let's do this. Good job. All right, now see if I mess this up.
No, it'll be great.
I have no idea. I think it takes you on like the staircase. You know, we're looking for spot. Yeah, go up there. Wait, are you on spot? Yes. Yeah, it's like up there, kind of around.
You have to go up the stairs.
Okay. Yeah, what's up?
All right. All right. It has been 3 minutes, so we're gonna do some more nomenclature. Don't worry, this is the last page, so we'll change subjects after this. So for our first molecule, we have a alcohol group that we should probably note first. And since this alcohol group is here, we know that it's gonna be given priority over all the other branches here. So with this information, we're gonna number our parent chain based on whatever gives our alcohol the lowest number. So here, we're gonna start at this carbon. So 1, 2, 3, 4, 5, 6, 7, 8. Pardon my bad handwriting. I don't really use iPads much. So now that we have our alcohol here as our 2, and we have clearly 8 carbons in chain, all we got to do is take our other branches. So starting with bromo, since it's the first alphabetically, we're going to take 5 bromo. And then go to our next one, which is 7 methyl. And finally take our parent chain, which is an octan. And since we have our alcohol at number 2, we're going to simply remove the E and replace it with a 2 ol. Everyone understand that? All right, sweet. So for our next molecule, we have a methoxy group, a chlorine, and an amine group here. And since this amine group is the only one that can be given priority, it's going to go at the back of the parent chain. So we're going to have to number giving this one the best priority. So for that, we're going to start naming from this carbon here. 1, 2, 4, 5. So we have a pentane with 4 for our chloro and 5 for our methoxy. So moving down the line, we have a 4 chloro. Be sure to spell your functional groups correctly because we do take points off of that, unfortunately. Followed by a 5 methoxy. And finally, I should have mentioned this beforehand, but my bad. But also we have to notate this group here as a functional group here. So this will be a N-methyl. And finally, we're going to put it in our pentane group, which is pentan 2 amine. I know that's a really bad handwriting, so that's hard to read. Let me know. So finally, we have a cyclohexane here, and we have another amine group. This time, it has 2 separate groups attached to it, which is a methyl group and an ethyl group. So obviously, it's a cyclohex group, and since it's an ethyl group here, it's going to go right in the front because alphabetically it's first. So we have a N ethyl, then a 1, 2, 3 N3 dimethyl group. Sorry about that. I did not anticipate the space I would need. And then finally, we have a cyclohex and 1 amine. Fair enough, fair enough. I'll rewrite that. Yeah. What?
No, like Loki just not.
Okay, just rewrite it.
Okay, let me just eraser.
I find it like unknown. I was just saying write it like basically different.
All right, sweet. Are you sure? Okay. Does this work? Okay. Oh, okay, that's sweet. All right. Thank you. So I'm gonna rewrite that again, hopefully in a more legible way. So we had our first N ethyl, followed by N3 dimethyl, cyclo X and 1 amine. Is that better? All right. Sorry about that terrible handwriting. I'll try and do better. Thank you. All right. Just 4 more, okay? So we have another cycloalkane. This time we have alcohol and amine on it. So since alcohol is here, it's going to get priority over the amine group. So this amine becomes an amino branch. So starting off with our number, we have 1, 2, 3. And writing that out, we're just gonna write it as 3 amino cyclo pentan 1 all, or cyclopentanol. Any questions? All right. We have another cyclohexane here. Of course, the alcohol is here, so it gets number 1 priority. So this will be our 1. And we're going to number it so that it gets the lowest numbers possible. So we have to go to the left. So chlorine will get 2, 3, 4, and 5. And with all these numbers in, we're going to go alphabetically with 2 chloro, 5 ethyl, 4 methyl, cyclohexanol. All right. Now we have another cyclohexane, this time with 2 alcohols, 1 on the wedge and 1 on a dash. And since we have only 2 groups, this is going to be one of our cis or trans configurations. And since it has a 1 wedge and 1 dash, that means it's just a trans configuration. So all you're going to do for that naming is just write trans right in the front with the dash, and then follow the same rules. Cyclo hexane because now we have two, so we're gonna write 1, 4, 4 diol. Oh. Am I doing bad? All right, don't worry, we have just one more and I'm done. So just one more, we have our alcohol once again. That's going to take number one priority. So we're going to name from the farthest right carbon. So 1, 2, 3, 4, 5. So we have a pentane. And of course, you have the amine group here as well. But since the alcohol is present, it just becomes another branch. So naming it, we have 5-amino, followed by 4-bromo, pentan, 2-all. Any questions with that? Yeah.
Let's see
The fourth one. All right. Yeah, I'll try and work on my handwriting before the next review session.
Well, next time we'll have reactors, so.
Oh, no. That's bad. That's worse.
No, log lines are easier to do.
All right. Wait, where? All right, what can I do?
Still call it and methyl over there.
Wait, you talking about the last one?
Yeah.
Yeah, it would be N-methyl. Correct. And then that would go like after the bromo, because that's like lowered alphabetically.
Yeah. Okay.
All right. Yep.
But what I'm sort of for the hexanol.
Yep.
Hexane, 1-all.
Yeah, hexane 1-all and hexanol are the same thing. That won't matter on grading. We'll mark it correct either way. All right. If there are no more questions, we'll do another 3-minute break and then we'll, oh, yeah, what is it? Oh. Okay, because we have one methyl group that's attached to the nitrogen group, and we just have one methyl that's all alone on the third carbon. And since they're both methyls, we just put them together to save time, essentially. Yeah. All right. We will do another 3-minute break, and then we'll have one last page, and you all are out of here. Yep. What? Well, they definitely have to.
Yeah, thank you.
Okay. Do you normally use an iPad? No, I just like I don't even look up everything. Also, I feel like it sounds very because they're like honestly, your handwriting's so not as like so like people would start thinking that. And also there's an answer.
You guys can have like perfect next time. I just kind of did it like really well. It just sounds like a separation. So like you can
Oh.
I know, I think it's today. I'm so bad. It's not
Lena, you there? Okay, okay. All right. Can you guys hear me? Okay. Now I'm gonna like quick review for the isomers. First, different compounds. Okay. You're gonna see like different molecule, but like consistent isomer, you're gonna see like different connectivity, which means you're gonna have different structure. For example, different number of rings or different number of branches or the groups. For the stereoisomer and then same compound, in the exam, you guys have like pretty much similar comparison. So technically, the professor gonna make it wrong. So I'm gonna like tell you how you're gonna do not gamble 50-50%. I'm gonna make it 100% gambling. When you compare with that, stereoisomer, think about side groups relationship. Like, or they are in cis or trans, or they have like totally opposite direction. Now we're gonna move on to the question. In that case, I'm gonna count how many carbon in here. 1, 2, 3, 4, 5, 6, 7. And then that is branch on the third carbon. In that case, 1, 2, 3, 4, 5, 6, 7. Okay, it pretty much looks similar, so I'm gonna name this. That is heptane for parent's name. And we have branch, which is 3-1-1. Shit. Okay. Dimethyl ethyl heptane. 1, 1, 2, and then these are dimethyl in here. It is same 1, 2, and then dimethyl and the 1. So in that case, we have exactly same IUPAC name, so we can confirm they are same relationship. For the second question, I can remember how many carbon and hydrogen. 1, 2, 3, 4, 5, 6, 7, 7. 1, 2, 3, 4, 5, 6, 7, 7. And I can remember hydrogen. 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12. And then there's a high hydrogen here. So totally age 14. For that, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we also have C7H14. For this reason, we can assume it is constitutional isomer. For these third question, it is kind of easy because we have oxygen in here, but we don't have oxygen in this case. So we don't have to number it, we just say different. First, it's Newman projection, so I'm gonna write down like Lewis structure first, and then compare to other structures. I'm gonna do that carbon is front, and the other is behind it. I'm gonna do red on the front carbon, like carbon, hydrogen, hydrogen. And the behind carbon, that connects CH3, ethyl group. And they're gonna take this for the second one. The front carbon attached to 2 hydrogen and 1 metal. The second carbon, I did wrong color. The second carbon that attached Ca to ethyl group, and then 2 hydrogen. In that case, we can name it for these two structure as 1, 2, 3, 4, or 1, 2, 3, 4. So it is like 2 methyl butane. But in this case, we do 1, 2, 3, 4, 5. So it is pentane. Different naming, but have same molecular formula. So we're gonna do constitutional isomer. For the fifth one, now it is like kind of annoying question, but we have to figure out how the side branches are related to each other. So that one, the CH3 in the chair is axial up position, And this methyl is equatorial position. And that bromine is axial position. In the Hayward structure, this methyl, we can see up if you're like hanging on the road, and then you see like, oh, this methyl, this hydrogen, that bromine. It's kind of like coming in front of you, and the other three groups is something like behind. Okay. Oh. Easy? Okay, guys, back, please. So for this reason, that is stereoisomer because they have different relationships. For example, like these CH3 are kind of this circling CH3 on the same plane to that methyl and that bromine. However, on the right structure, that hydrogen has the same plane with these methyl and bromine. So it is different relationship with each other. I say stereo isomer. Now, for this bond structure, I'm gonna count how many carbon here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. See 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See 12, okay. We have different number of carbons, so we can say it is different. Now we can go back to some 7 problem, but I'm kidding. I'm gonna go back and I'm gonna make one more problem and I think about kind of like challenge to you guys. So I'm gonna get rid of this oxygen. And then there's the CH3. I'm gonna write down another short confirmation. Now, what are their relations to each other? Okay, no thoughts. So now in that case, I'm gonna write down which one is axial and equatorial opposition. This CH3 axial. So two side groups gonna be equatorial opposition. We have these two are equatorial opposition. So the right alternating with each other are axial opposition. So that CH3 is supposed to be equatorial opposition. Yes. So we can say these CH3 groups are on the same plane. Now I'm gonna convert this Lewis structure, this bond structure to the chair structure. I would say wedge is like axial opposition in this case. So I'll set up that for CH3. So we said it is axial opposition, then these two are equatorial opposition. And the right next two groups have axial opposition. And the last group is supposed to have equatorial opposition. For this reason, to have axial down position for CH3. If we compare these two structures, these two CH3 are in a different position. So you say this cone stereoisomer. Are good? Okay, cool. For the seventh question, these two CH3 are cis. These two CH3 are ortho cis. These are pancake weight. So I would say the same. The last is another thing. We are looking down this structure and the CH3 are coming in front of you, and these CH and the bottom of the CH3 are behind you. For the flip flop, these CH3 are coming in front of you, but these alpha groups are kind of like behind or away to you. So we will say it is stereo isomer. Any question? Cool.
Okay, wait, don't touch anything.
Do you have any questions? You can come down here. Yeah, thanks.